Evening, everyone. We're now going to kickstart the next presentation in track 1. Before we begin, a quick introduction of our speaker for this slot, Mr. DinoDaiZovi. DinoDaiZovi is an information security professional, researcher, and author. He has been working in information security for over 8 years with experience in red teaming and penetration testing at Sandia National Laboratories, at Stake, Bloomberg, and Matasano. He currently manages information security for a technology-based finance firm in New York City. As an independent researcher, he is a regular speaker at industry, academic, and hacker security conferences, including presentations of his research on hardware virtualization, assisted rootkits using Intel VTX, Takama Wireless Client Security Assessment Toolkit, and offensive security techniques and tools at Black Hat USA, Microsoft Blue Hat, Kensec West, the Usenix Workshop on Offensive Technology, and DEF CON. He's perhaps best known in the security and Mac communities for winning the first Pwn-to-Own contest at Kensec West 2007. And today he's talking about macOS exploitation. Join me in welcoming DinoDaiZovi.
Thank you, everyone. This is my first time in Kuala Lumpur, and it's pretty awesome. So I had roti canai for the first time a couple nights ago. That's amazing stuff. I think I'm going to have it every night while I'm here. So I'm going to be talking about hacking Macs. So if any of you wanted to win the Open Hack competition, and you're sitting on a vulnerability, just had trouble getting the exploit to work, you've come to the right talk. If you don't have a vulnerability, well, there's a couple hours the rest of the day, you can find one and you'll be fine. So why are we going to talk about Mac exploits? Macs are becoming way more prevalent, especially in consumer laptops. For instance, in the US during July and August, 20% of the laptops sold in US retail were Mac laptops. And so especially in the last year, there's been an explosive growth in them. And just in various areas, like in New York City, where I live, there's almost everyone has a Mac laptop. It's kind of silly. You very rarely see someone with a PC at a coffee shop or something like that. And even here, you see a lot of people with Mac laptops. And because the operating system is very different, it's a good idea to take a look at how secure it is to various attacks like malware and all the other things that affect other platforms. And one of my concerns is that even though malware does not currently target Mac operating systems, there's no reason why it couldn't. Mac is significantly lacking in a lot of the defenses that other operating systems have, like ASLR, NX, stack and heap memory protections, and basically they need to step this up pretty quickly before it becomes a problem. And there's also this very big difference in perception about the security of Apple products. And the way I explain this is that there's a difference between safety and security. For instance, depending on where your house is, it may or may not be safe to leave your door unlocked. No matter what, it's always insecure. Someone can always walk in through the front door, but you may or may not do it. And surfing the web with Safari on a Mac is like leaving your door unlocked. You're just hoping that nothing bad happens because there's nothing stopping it. So I was reading Nico Weissman's blog. He works for Immunity. And he said to make your presentations more interesting, you should use lots of pictures. And so all of his presentations have these really awesome pictures of bugs. And so I'm going to use pictures of ferocious cats. So also with OS 10, the last operating system was called, 10.4 was Tiger. So we're going to start with the Tiger. We're going to move on forward. So I'm primarily concerned with memory corruption vulnerabilities. This is the larger umbrella that describes many types of exploits, ranging from the simple buffer overflow to integer overflows, out-of-bounds array access, uninitialized memory use, just all this stuff that lets you corrupt memory and application state and ideally execute code. Other operating systems have discovered that this is a huge problem. This is enabling web drive-by downloads, system compromises, and so there's a variety of defenses that have been shipped in other operating systems. I'm going to talk a little about in case anyone's not familiar with them. These are address space layout randomization, non-executable memory, and various stack and heap memory protections. I'm also going to talk about how OS X tries to do these, but it actually doesn't. They kind of try and get them as marketing bullet points, but they sort of fall flat in their actual implementation. So first off, address space layout randomization. Main idea here is that all memory corruption exploits, almost all of them, require hard-coded memory addresses. So these might be the return address that you use for a overwritten in a stack smash for the overwritten return address. Might be other things you use, overwritten pointers, various other things. All of them are hard-coded memory addresses. So ASLR just shuffles memory so that an attacker has no way of knowing what these are, or it's very difficult, so they have to guess. And basically, in guessing, they may crash the application if you only have one try before the application crashes and it doesn't restart itself. Or it'll just, at minimum, it'll stop a worm from spreading. Because if 1 out of 256 tries fails, worm's not going to get off the ground, but an attacker can just try it multiple times, and they may still succeed. This was pioneered by the PAX project for Linux, which is the first known implementation. And at this point, like for Linux, I'll just talk about Ubuntu. Ubuntu ships with full ASLR. It's randomized dynamically for each process, very solid. Windows Vista has full ASLR. It's randomized at system boot, so it's the same if you restart the process, and it's also the same for all processes on the system. Except for some elements of the address space are moved around a little more, like the stack and the heap. They have these little offsets that are purely random. But in particular, DLLs are at a fixed place. Leopard, it actually, for OS X Leopard, it's really not accurate to even say that they have ASLR. What they have, and even Apple admits this, is they have what's called library randomization. And what this does is this just shuffles the libraries on the system whenever the operating system or the applications are updated. So I'm going to talk a little bit more about how this works. So there's a command line tool called update DYLD shared caches. And the interesting thing to note about this is they did not implement this for security reasons. Basically, they had this for optimization. It's called library pre-binding. So instead of linking all your libraries when the process launches, which can be time-consuming if you have a lot of libraries that you depend on, what they'll do is they'll do what's called pre-binding. They'll just take a bunch of libraries, merge them all into one big image that are already linked together, and then in most cases just load that whole thing up. And just because it was essentially free, they decided to randomize this. Because they're gluing them into a big image anyway, it doesn't hurt to put them at random places. And so what this is this creates a shared region cache file that's stored on the file system, and this is basically loaded into every process at launch time, and then when the application needs to load a library, if it's already in there, it just uses the one in the cache. Otherwise, it actually loads the library and will do the linking and things it needs. So keep in mind that these are randomized, or these libraries that the application may use are randomized, but there are several important things that are not randomized. That includes the base address of the executable itself. Most importantly, the runtime linker, DYLD, is not randomized. It's always stored at the exact same place in memory. And it's what is used to link everything else, so you'd think you'd want to randomize that the most. A piece of memory called the COM page, which is a bit of code that is shared between the kernel and userland. Stack segments, heap memory, memory allocated with mmap. None of these are randomized. These are all at the exact same location. And so as I mentioned on the last slide, when the shared region cache is created, they actually store a map of this cache. And it's nice in a nice text-readable format, or human-readable text file, that you can just go through and see which libraries are loaded in there and where they're loaded in memory. So for instance, for a local vulnerability, you can just, you don't need to worry about randomization, one, because you can just look at it in one process and see where libraries are loaded in one process. You know they'll be loaded in the same place in a target process. Or you can just read this file. So the next security feature that Apple kind of half does is non-executable memory. The main idea here is that code execution exploits are taking advantage of the fact that writable memory that's supposed to be data gets loaded with machine code, and the application gets tricked into executing it. Well, you should never be executing data bytes as code bytes. So the idea is it will mark data pages as non-executable to make sure that they aren't executed. And the reason this is special is that x86 processors prior to some Pentium 4s and the Intel cores didn't actually support non-executable memory. Pages were readable or writable. If you could read a page, you could execute code from it. And because of that, the PAX project, the same project that invented ASLR, they used a very creative technique to implement truly non-executable memory by desynchronizing the TLBs on an Intel processor, so that basically if you tried to access a page and page it in that was as data, they could detect that versus if it was tried to be paged in as text. And so this is implemented now in a variety of operating systems, Linux, with PAX and JR security patches. Windows has DEP, which will do hardware DEP, where it's supported on the processor, or software in other cases. OpenBSD has this as well. And the real implementation of this uses, as I mentioned, the NX bit that's supported in more recent processors. So the hardware is there, and it's on every processor that Apple ships, or every x86 processor that they now ship, but they barely use it. They just set the NX bit on stack segments. So at least they do it on the main thread stack and all the additional thread stacks, and that'll stop the most basic Stack Overflow, but really nothing else. It's actually really easy to get around. And so that's what we're going to do. So one of the things that I developed was just a very clean stub that you can take any Stack Overflow, and instead of just returning into, instead of just using a return address to return into a library, then back into your code, you can just paste this stub, and it will do all this, black magic to copy your executable payload to the heap and execute it from there. And the way it does this is it depends on three what I call non-features, three artifacts of how Apple does things. Like I mentioned before, their library randomization does not randomize DYLD. So DYLD is the shared linker. Same thing as shared linkers on other Unix operating systems, and it's been at the same start address since the beginning of OS X time. And one of the other things it does is so in Leopard, because all the libraries are randomized, any shared library functions they used to use, they can no longer call the libraries for. For instance, in Tiger, libsystem, which is like libc for OS X, but with like a bunch of other stuff thrown in there, used to always be at the same location also. So they would just link DYLD and libsystem together, and so they could call functions, in each other without really having to link, because the linker is the first one that's loaded. It can't link until it's done executing. So what they do in Leopard is they just basically paste in the implementation of several library functions into DYLD. And one of these is the function setJump. SetJump and longjump are used to basically save your executing context to the stack, and then you can resume it later on. It's for like a really long-range go-to. And so basically we're going to use that in our stub to kind of use it in a very tricky way to gain control. And the other thing we're going to use is the fact that Stack Overflows on x86 can use what's called return chaining. So it's basically like returning into libc multiple times. Instead of returning into just one function, because functions on x86 take their arguments from the stack that the attacker has completely overwritten, you can return to one function, and it's going to pop arguments off the stack from the overflown buffer. And so you can return to one function, and then another, and chain these all together to basically, essentially, write a program all through kind of backwards returning. So it's kind of tricky. And the return chaining, I kind of have this admittedly somewhat crappy diagram at the bottom of my slide that shows kind of your overflown stack going from left to right. You overflow the saved frame pointer, and then you smash the return address, which is your saved EIP, and then right after, so basically, if you return from that overwritten EIP into a function, like at the top of the function implementation in a shared library, it'll pull off an argument from that following it. So that's the return 1 arg. And then when that function is done, it'll return to return address 2, which will pull return 2 argument off the stack. And basically, you can use this to call any functions that take 1 argument over and over again. And so what this stub does is, like I mentioned, you just basically take it, align it with EBP and EIP, and it just encapsulates all of this logic that will return into setJump. And the main idea is, so because there's no ASLR, you can choose addresses at will, and we can return into setJump, and we'll just choose a writable memory address. And so I just use a memory address in the writable data segment of DYLD. So what that does is that basically writes the value of all our registers to this hard-coded memory address. Because we've also overwritten the saved EBP, that's one register that we can control. So I can return into setJump, which will write all my registers to a piece of memory, and then return from there to that memory, and it executes the value of the EBP register as CPU instructions. So that gives me 4 bytes of controlled executable bytes. I'll basically do this a couple times to gain more control, and then finally we'll return into stirdup, which takes a string and copies it onto the heap and returns that buffer, and we'll call stirdup on the rest of our attack string, which contains our payload, and then execute that instead. So to kind of go into a little more detail, like I said, there's an implementation of setJump in DYLD, so we can hard code that address, and we'll know where it is for that version of OS 10. So we're going to jump into that, copy all our registers to a chosen writable address. We're going to return to 24 bytes past that writable address to execute 4 bytes from the value of the EBP register. And because x86 code is so compact, those 4 bytes actually let us do something useful. We need to adjust our stack pointer to make everything work. So we'll just adjust ESP, and then we'll execute the pop A instruction. The pop A instruction will basically load all the CPU registers from the stack pointer. So it'll, from our attack string, load up more registers, and then I'll execute ret, so that the ret to return to the next address on the stack. And so this lets us kind of keep bouncing along. And at the end of this buffer on the first screen here, I have the 12 bytes of x86 code. So those are actually, when you execute the pop A instruction, it'll load that memory into registers. I think if I recall correctly, it's the EDI, ESI, and EBP registers. Yeah. So, and this time, we're going to do the same thing. We're going to jump back into setJump again, and then return into our jump buff, and that'll give us 12 bytes to execute of chosen instructions. What this does is, again, it has to adjust our stack pointer just to make everything work out correctly, and it's going to take the address of ESP plus 0xC, which is essentially the pointer to our payload that follows the stub, and then it's going to push that onto the stack so it can be used as the argument to the next function that we're going to call. Overflows on QuickTime are a little more difficult to do, but that doesn't really stop anything because QuickTime also has plenty of heap vulnerabilities, and heap protection is not exactly something that Apple can just build into one binary. It requires actually changing the system level heap. So let's move on to how Apple's heap is created. And what I say about the heap is that its level of security is very 1999, which is essentially true because they wrote it in 1999 and just haven't really changed it since. So they call it the scalable zone heap allocator because it grows the heap by different size zones. So depending on the size of your allocation, it's basically divided into multiple subheaps. So for instance, if your allocation is under 496 bytes, it'll go to what's called the tiny heap. And if it's a little larger, it'll go into what's called the small heap, or large and huge, respectively. And the way that it does this is each heap is divided into fixed-size blocks that it calls quantum, or quanta, be plural. And it will, any allocation is rounded up to the nearest, or to the next largest quantum size for that region that it's assigned to. And so basically, why you need to know this is depending on the size of buffer that you're overflowing in a heap overflow, that'll change how the heap actually behaves. And for the tiny and small, most of the buffers that you'll overflow are going to be under 16K. And so basically, they operate mostly the same. So these are where we're going to focus a lot of our attention. And also because everything above that is a little more custom there. Instead of using fixed-size quanta blocks, they just allocate pages directly. So it's less like a heap and more like sort of just relying on the operating system memory allocator. So like other heaps on Windows or older ones for Linux, they have a system of free lists to basically organize free heap blocks. And if there's a memory allocation for a buffer of a similar size, it'll allocate it from the free list. It'll allocate it from the free list instead of assigning it to a new heap. So these free lists are stored in a free list array of 32 elements, and basically that organizes all the free blocks based on size into, based on their multiple of the quantum size. So for instance, this picture shows the tiny region free list array. And so there's, on the left we have the array, which is basically 32 elements, 32 elements. And for instance, the first one is allocations up to 1 times the quantum size. Second element's 2 times the quantum size, and so on. And then the last element in the array is anything larger than 32 times the tiny quantum size. And each of these array elements point to a linked list. And these linked lists are all the free blocks. And so the important thing to understand and remember about heap overflows is that these linked lists are not external to the heap allocations. These are in the heap blocks themselves. And so this is the crucial vulnerability of kind of the classical heap overflow, is that these pointers that link the linked lists are in an attacker's reach. If you overflow one buffer into the next, you are overwriting, and that next heap block is a free block, you are overwriting this heap metadata, the previous pointer, the next pointer, and the block size. So, like I said, basically this metadata is stored inline, which is basically the source of most memory corruption vulnerabilities. For instance, Stack Overflows have inline return addresses inline with data. Those can get overwritten. Heap overflows have inline heap metadata. Those can get overwritten and corrupted. And so basically what you're doing is you just basically overwrite the heap from the overflown buffer, hoping to find a block that is considered a free block, and that's once you can overwrite the previous and next pointers. And in practice, what you'll do is just have your values for previous and next just repeated 1,000 times, so that if any of those are aligned on a free block that gets removed from the free list, you will actually gain control or perform the 4-byte memory overwrite. And so the way this works is that because it's a linked list, it does an assignment of the previous to the next to remove it from the linked list, and this lets you do a 4-byte overwrite, which I'll cover in a little more detail in a couple slides. And one thing to keep in mind is the heap is a very runtime dependent data structure. It's very dependent on how the application is running now and in the past. And if as an attacker you can control or influence allocation sizes, and when these allocations happen, this will allow you to manipulate the heap and basically line things up to make exploitation much more reliable and much easier. So kind of give a picture to this. On the left, we have an adjacent in-use heap memory block and free block before there's an overflow. So in the in-use block, there's just data there. And the free block still has the values for the previous pointer, the next pointer, and so on. And then after we overflow the in-use block into the free block, we choose new values for the previous pointer and the next pointer. And what this will let us do is basically, for one value for the previous pointer, we specify the value. For the next pointer, we specify the memory address that we want to write that value to. This is commonly referred to as what and where. What you want to write, where you want to write it. And one thing to keep in mind for the next couple slides is you don't actually write the memory address of the target. You have to write the memory address that's basically the checksum of the target. The heap was somewhat clever in wanting to prevent or detect accidental heap overflows. Because heap overflows are a big pain, because if you're overwriting past the bounds of a buffer, you don't know when the application will crash. When you have an accidental stack smash, it crashes immediately. On an accidental heap smashing, it just corrupts memory, and then it might crash 5 minutes later, or it might never crash at all. And then you run it again, it may or may not do that. So to make debugging a little useful, they basically, on all heap operations, they, quote unquote, validate these pointers to make sure they haven't been overwritten. And the checksum they use is very simplistic. They make use of the fact that any heap pointer is going to be at minimum to a 16-byte block, so it'll be aligned to a 16-byte memory address, which means that you have 3 unused bits, 3 unused least significant bits that'll always be 0. And so they do is they shift and set, which means basically that they can verify a heap pointer just by ANDing it with this value here, and making sure that none of those crucial bits, the 2 least significant and the 1 most significant bit, have been overwritten. What they'll do is whenever they do a heap operation, they'll do this to the next and the previous pointer. And to remove the checksum, they just shift and AND. But what does this let us do? If you look at the address space of a process on OS X, there's a lot of interesting things in the lower part of the address space. And these lower addresses have a null byte as the most significant byte. But in other heap implementations, you often can't write to these because you're overflowing via a string operation. The null byte will signal early termination. So you can't do that. However, because of this checksumming, they basically get rid of that annoying limitation for you. What this will let you do then is target these memory addresses that have a null most significant byte and overwrite them if you want. And there's some actually very interesting stuff in there. One is called the imports table. The imports table has function pointers to all the imported functions that an executable uses. So if you can cause a heap overflow, you can overwrite the pointer to printf, and so the next time the application calls printf, you gain control. If the application is written in Objective-C, the Objective-C memory segment in the executable has crazy amounts of information. It actually has the entire Objective-C class structure for the executable. You can overwrite things in here. You can overwrite method pointers, and this will let you gain control whenever an Objective-C method is used. Other malloc regions are stored in the address space with these addresses. These also have function pointers in them. There's a bunch of stuff you can do. So just to review the classic heap metadata, it's called a write for. This is just writing one value. Halvar Flake at Black Hat 2002 was the first to really talk about this. And how this works is if you have two allocations of two different sizes, A and B, and then B is freed, and then you can overflow A into the memory that was previously occupied by B. And then you can cause that memory allocation for that same size as B. This is in step 5. That'll cause B to be removed from the free list. And then basically when it's removed from the free list, that memory that you've overflown into the space occupied by B, which is the front and previous pointers, or the previous and next pointers, gets used, and it assigns the previous to the value of the previous pointer to the unchecksummed value of the next pointer. That's writing what you want, where you want to do it. Perhaps a more creative attack was presented by Oded Horowitz and Matt Conover at CanSec West 2004, where they expanded this by adding a step. So you can see that steps 1 through 5 are the same, but 6 and 7 are different. And again, this is what you need to do is, an application isn't going to be this ordered, but you may be able to affect these steps by altering the size of your request. If it's a network server, you can change, like for instance, an RPC server, you can change the size of your request, and that'll change the size of these heap allocations. And so you can sort of, order these by having multiple threads that make requests and keeping the first connection open so that it doesn't free it, so it just is a malloc and not a free. And you can basically order these until you have this sequence of operations. But the cool thing that this does is after the write for happens, what it also does is it writes the heap implementation, writes the value of your of the next pointer into the free list, so that the next allocation to the heap for that size, instead of returning a pointer to a heap block, they'll actually receive the pointer to a piece of memory that you've chosen. So instead of being able to, if you have a heap overflow like this, instead of being able to write 4 bytes where you want, you can write as much data as you want, because you can get the heap to return a pointer to somewhere in memory that you want, and then the application will actually fill this buffer using data that you specify, allowing you to write whatever you want to wherever in memory you want it. So this is a kind of a much more effective attack. But we're still talking sort of early 2000s. And this is just to show you, so this is kind of the state-of-the-art attacks around that time. And this is to show you that these are still very reliable and very effective against OS 10. But of course, the new stuff also works. Heap feng shui, so like I mentioned, a lot of these previous techniques assumed that you had limited influence over like a remote server, for instance. A lot of these were pioneered using vulnerable Windows RPC services as their test beds. However, these days, most likely you're attacking a web browser. And in a web browser, you have JavaScript, you have all these other things, and you have much more influence over the allocation pattern of the heap. And so you can do what's called heap feng shui. And what you'll do with this is you'll basically have a loop that does a lot of heap allocations of controlled sizes. And so if you know that you overflow a block of size X, and that there's an object of size Y that has like a function pointer in it, you can basically massage the heap until you have a bunch of gaps of size Y. And so then, when the application allocates one of these objects of size Y, it'll place it in the gap, and then you can overflow from object X over Y, and you know that instead of attacking the heap metadata, you can overwrite a function pointer and gain control directly. This is the attack that's commonly used against modern Windows systems because they have heap protection. They protect all their heap metadata against this, against the exploitation of the previous methods that I talked about. And this is a way that you get around it by attacking the application data directly. But it actually works very well on OS X as well because it just allows a greater level of control. And Charlie Miller, who will be speaking tomorrow on owning the iPhone, he used this to win the Pwn to Own contest at CanSec West this year. All right, so moving on to, we got our next angry cat. This is the angry leopard. And we're moving on to exploit payloads. So, okay, so it's pretty easy to write exploits on OS X. What else can we do? Unfortunately, a lot of the tools don't really work very well for OS X. For instance, using Metasploit, you have DLL inject, you have VNC inject, you have all these shellcodes that work really well for Windows. And actually, right now, a lot of their payloads are actually broken for x86 Macs. Or they work on some processes and not others, because there's various things like the vfork system call that they don't do anymore. Some of the encoders are broken. I'm working on fixing all these. But instead, I also wrote my own. And so the basic building block of this is the Mach-O function resolver. And what this does is most Unix payloads will execute system calls directly because it's really easy. You just load up a register, do an interrupt, and you're executing the system call. This is great for sockets and stuff, but what if we want to do more than that? If we want to do more than that, we have to actually use the shared libraries. And so the way we do this is we actually have to do our own linking by hand. And again, because DYLD is loaded at the same address, we can basically just parse memory, find the symbols that we need in the linker, and use those to build a bridge to link everything else. And this is a very common technique that's used in Windows shellcode to grab symbols out of kernel 32. We use the same technique. We hash the symbol name with a very compact hash, and then we compare that to the hash in our shellcode, and then we'll just call that function pointer. And how we'd use this to build other things is DLOpen is basically the Unix equivalent of load library, and that exists in DYLD, so we can just use that to load another library, and then use DLSym to load it to find the function that we want, and then call it. A lot of the early shellcode for Windows would always use load library and get proc address to kind of load up everything else that they needed. So this is great to load up functions one by one. But, for instance, how would we say we wanted to call a Objective-C framework. How would we use this to call Objective-C methods? It's a lot of very painful work, which we don't want to do. So what we're going to do is we're going to leverage the linker itself to actually load our shared library for us and do all the linking to Objective-C frameworks or whatever other libraries that we want. And so I built a staged bundle injection payload. So like other stage payloads, basically this is split into stages so that the first stage is a little smaller in the exploit, and it will download additional code as it needs and execute that. So the first stage establishes a connection with the attacker, reads a fragment size, reads that many bytes into M-mapped memory, and this memory is mapped read-write executable, so it can write into it, execute it, whatever it needs. And then it'll treat that memory as a subroutine that takes one argument, being the socket. It calls it, allows it to do whatever it wants. And this is technically enough for us to do anything we want, because we can just write assembly code, and then just in a loop, it'll download the assembly code, or download the machine code, execute it with our socket, allow us to build other things, and then return and just keep doing this until we're done. But that means we still have to write our stuff in assembly. So instead what we do is we'll use this to download a second stage. And so that second stage is the machine code fragment that will do something very similar. It'll just read a size from the socket, and then which will be the contents of a file, and it'll read that file directly into memory. And this is where Apple really helps out. If anyone's familiar with the DLL inject tools from Metasploit that Matt Miller wrote, they had to do some somewhat clever, they had to do some very clever things to get to do diskless bundle injection. And to do this, they had to hook some of the very, underlying functions so that when you did NT-open of a special file name, it would actually load the contents of memory rather than loading it from disk. Well, Apple actually provides this functionality for us. In DYLD, there are these two great functions, NSCreateObject file image from memory and NSLink module, that we can just basically, we give it a pointer, we say create an object file from this memory, and that loads it as an object file. And then we just say link module, and that does all the linking stuff for it. So all we do is just take a compiled shared library, which are called bundles on OS X, just slam it into memory, call these two functions on it, and that'll be just as if the application had linked and loaded that library itself. And then what we'll do is we'll just, because we want more control over its execution, we'll look up a function called run in that library and run it. Yes, go. And so what that does is that basically loads our third stage. And our third stage is written in C. This is a compiled bundle, which I guess I should explain a little more about what a bundle is, because on OS X, it's a very overloaded term. A bundle could be a directory of things. For instance, an application is technically called a bundle because it has the application binary and all these resources in there. But when you talk about the linker, a bundle is a special like shared library format that is meant to be used as a plugin. So, but what it means is just a lot of the stuff, a lot of the linking assumes it's a special format. We just compile it in a special way, and allows us to use these APIs to link and load it really easily. And what this lets us do is write whatever we want in C. We can use C, C++, Objective-C. We can specify any frameworks we want to link to, and it'll just run. And this lets us do pure memory injection. It's never written to disk. And the bundles are actually still pretty compact. Just a simple hello world bundle that just prints something out, really does nothing, is only about 12 kilobytes. And so basically, this is what it looks like. This is just the basic skeleton code for the three functions in the life cycle. We have a constructor that is called implicitly when it's loaded. We have a run function that is called explicitly by our payload. And we have a destructor function that is called implicitly if and when the bundle is unloaded or when the application is shutting down. And all we have to do to compile this is just give it the bundle flag, and we now have a injectable bundle. And so, well, what would be an interesting payload that we can use this for? The first thing that came to mind was taking advantage of the fact that every Mac laptop has a camera now built in. So this is the take a pic of the VIC. There's basically QuickTime allows very easy access to the camera, and there's even a bunch of open source code to do all this. There's an Objective-C class called Cocoa Sequence Grabber that's actually implemented in a plugin for MacFuse. Basically, it was really easy to use this to just capture a simple image, just a single image from the camera, and we can send it back, which does actually turn the light on briefly, but it's kind of hard to notice. It's on for like 1/10 of a second. So if you're not exactly paying attention, you won't see the light go on. And that's just basically the Objective-C code that was required. Really pretty straightforward stuff. So these modules are in private beta right now, but I'm going to release them for the Metasploit project the next coming weeks here. Want to make sure that the whole that at this point no one believes that you can't write exploits against OS X. But kind of go through I wrote up some of my favorite exploits. The first one is one that kind of slipped through the radar, that it was fixed very quietly after the first Pwned contest at CanSec West of 2007. This would have been a really good vulnerability to win that contest with, because it was remote root out of the box through the firewall. If you turn the firewall on with all the strictest settings, you could still get owned by this. So it's probably the most serious vulnerability that OS X ever had, but no one really knew about it. So that was a fun exploit. Wrote up a QuickTime exploit for Tiger and Leopard, and this uses the execute payload from the heap stub. So it's a good example of how you can use that in a real live exploit. Also the QuickTime Java to Qt pointer vulnerability. This is what I used to win the Pwn to Own contest in 2007, which is also another really great vulnerability. They let you just read and write arbitrary memory across the full address space from a Java applet. So once you have that, it's really game over. And the two payloads that I talked about, the staged bundle injection and the iSight photo capture. Okay, you have to forgive me because I'm going to have to make up some time with some of the more complex stuff. So the last section I'm going to talk about is local bundle injection. On Windows, the remote thread injection is a pretty common technique, which lets you load a DLL into a new process and inject a thread, and you can basically load a DLL and call functions in it. I had to write all this stuff in OS X by hand. And so to understand how this works, you have to know that OS X is this hybrid operating system that it uses parts of Mach and FreeBSD. And it's essentially the top half of FreeBSD ported to the bottom half of the Mach kernel. And what makes it really interesting is that there's a ton of different interfaces into the kernel because of the sort of dual ancestry of Mach and BSD. You have traditional BSD Unix system calls, which are executed with positive system call numbers. But if you use negative system call numbers, these become Mach system calls. And these send basically system calls directly to the Mach part of the kernel. There's also BSD sysctls and IOCTLs that you can use to communicate with it. But the Mach kernel primarily uses RPC to communicate. And so Mach is built with RPC messages to communicate between different processes that they call servers. This was the main idea of a microkernel-based operating system. And you communicate even with the kernel through the same mechanism. And OS X still uses that for a lot of things under the hood. And this uses Mach IPC, which is built on what are called ports, which are these unidirectional message passing-based IPC mechanisms. And different processes have rights on, or different tasks have various rights on these ports. So you can have a send right on a port, which allows you to send messages to it. But only one task may have a receive right on a port, which essentially gives it ownership of it because it can receive those messages. But the entire security model of Mach is based on these rights. So for instance, if I receive send rights on the port for another task, that means I can send messages to the kernel about that task and read and write its memory, create threads, and do whatever I want to it. It gives me full ownership of it. And there have been a number of vulnerabilities in OS X that arise from the discrepancy between BSD processes and Mach tasks. So here's kind of a diagram of how they interact. A Mach task has the Mach threads in it, the list of Mach ports, and it also owns the virtual memory. The BSD process, which is what you're used to interacting with, kind of encapsulates all of this, in addition to the BSD-specific things like file descriptors and so on. And there's a way to map between the BSD process and a Mach task. These are the two system calls called task for PID and PID for task. Task for PID was very fun, has a very fun history as well. But also keep in mind that a Mach thread and a POSIX thread are very different. So if you can, we're going to create Mach threads in a remote process, which are supported by the Mach system calls. But once you call a library function in that thread, it's going to expect to use POSIX thread local storage, which doesn't exist, and it's going to crash. So here are kind of the system calls that we're going to use. We're going to create a task. We're going to create a thread in a new task, and then use the direct memory allocation to allocate memory in a different task, deallocate memory in a remote task, and then read and write memory from it as well. We're also going to use the secret sauce of mock exceptions. These are how debuggers on OS X work and why GDB has to do a bunch of special stuff. Basically on OS X, ptrace, the normal debugging interface that Unix systems use, is essentially broken. Doesn't really do anything because everything, all this functionality is implemented using the mock, direct mock system calls that I talked about and mock exceptions. Unlike exceptions in like Windows, for instance, or Unix signals, you can actually handle these by a thread in another process. And so what you can do is you can attach to a thread or attach to a process and say, I'm going to handle exceptions for this thread or for this process. And so when there's an exception, it'll first get handled to the accepting threads exception handler if it exists. And if it doesn't handle it, it'll send it to the tasks exception handler. And if that exists, and if that doesn't handle it, it'll convert it into a Unix signal and send that to the BSD process. Really, really ugly, but it lets you do some cool things like the crash reporter on OS X is this global process that sets itself as the exception handler for every task. So if any process crashes, it gets a message saying, oh, this process crashed, and it can write the crash dump log to your file system. Or it'll pop up, most often you'll see it by it popping up a dialog saying this application has crashed, what do you want to do? And so to inject a mock thread, what we do is we gain access to a task port. So we use task for PID for this, or you can use a local attack to gain access through a vulnerability. And then you just allocate memory for the thread stack, and we have to paste in some code as a trampoline. And then we create the thread, assign the registers for that thread, so that it'll execute the trampoline using that stack segment that we've given it. And what this trampoline does is promotes a mock thread into a POSIX thread. And basically by reusing some functionality in the libraries, we can do this by just calling pthread set self and cthread set self. These will execute the system calls into the kernel to set the kind of magic registers like the GS register and various other things so that all the other thread function calls know what to do when they need to access thread local storage and things like that. And we can use this, did I talk about, oh yeah, so, and so the way we're going to use this is we also need to use exception handling to catch our return values. So we can inject a thread that'll call a function, but we don't know when that function terminates or when or what the return value is. And so we'll just have that function return to a known bad address, and our exception handler in the injecting process will catch it and obtain the return value. And then we can basically use that to call remote functions at will in the remote process. And from there, we can do deal open, deal sim, deal close to load a bundle from disk and inject it into memory and do whatever we want. Or we can inject the contents of a bundle file directly into memory, just like we did for the exploit payload. Call ns create object file image from memory, ns link module. That'll link it up and send it going as well. And then once we have this injected, there's a variety of things we can do. We can hook functions and Objective-C methods to log SSL traffic from Safari, log chat messages from iChat, do any of these things. These are just what I've implemented so far. So the final remarks on our final ferocious cat. 64-bit processes are allowed on OS X, and these actually, ironically, make exploitation much more difficult. And because this allows them to break backwards compatibility and just do new things. For instance, page permissions are actually enforced, so that if it's not executable, you can execute it. All the addresses contain 2 null most significant bytes. This makes it really hard to hard code these addresses in because those 2 nulls will either truncate a wide character copy, or they'll also terminate an ASCII string copy. And while you can use the trick of an early termination of a string to kind of use like the string copy function to write out a null most significant byte, if there's 2 null most significant bytes, you can't use this trick. Also, very importantly, function arguments are passed in registers. You can no longer use the return chaining. And so basically, a lot of the techniques that have been built up for other operating systems just won't work on 64-bit processes. And as OS X starts using more 64-bit processes, even though they don't have a lot of these security defenses, this will make exploitation much more difficult. But at present, the very few security-sensitive processes on Leopard are actually 64-bit. The only one is Apache. For instance, your web browser, still 32-bit, still easily exploitable. Snow Leopard is the next release of OS X that's supposed to fix a lot of these things. They say it's a security and stability upgrade. And they say we're really not going to implement many new features. But are users going to pay for a new operating system with just security fixes? It's hard enough to get users to upgrade to more secure versions of operating systems, even if there's other features in it. So that's yet to be determined what they do and whether people will adopt it. In conclusion, OS X is vulnerable to the same types of malware attacks as Windows, even though we aren't seeing it yet. And because it's increasing market share, it is becoming at more risk for these attacks every day. And it doesn't have these exploit defenses that other operating systems have. But what makes it fun is if you haven't gotten into writing exploits yet, because a lot of these features are making it a pain in the ass, well, just write them for OS X, because you don't have these things to contend with. And so, writing exploits for Vista is really hard work. Writing exploits for Mac is fun. So that's all the time I have. I went over, and the thing tells me I don't have any time for questions, but I have a minute left. So if you have any questions, you can find me afterwards. Yeah. Okay. Thank you very much.
Thank you very much, Mr. DinoDaiZovi. Moving forward, we're going to cap off today's presentation in track 1 with Anthony Borowski and Jim Javedi talking about Hacking the Bird in the Sky 2.0. Give us 5 to 10 minutes to set up, and we'll be right with you. Thank you.